Hello, everyone. This is Olivia. I want to do a shorter video on tutorial 3B and about topic modeling. Um, I've been motivated by projects including um, PhD students projects and capstone students projects to apply topic modeling and also gradually look into the methods and to enhance the methods. But so far, I have only been able to work on applying. So this tutorial will be primarily about applying topic modeling in R, and I think there's a lot of potential for it. I'm still at the initial stage of experiencing and exploring the use of some of the algorithms. So I won't take too long to talk about the method, mainly about applying it. And in the context of what we've been doing in tutorials and assignments so far. But before we go to tutorial, I just want to quickly come back to the unsupervised text mining approaches, in the sense that when you are limited by your data, you cannot do supervised learning with textual data. Then there are other familiar unsupervised data mining methods we can try. And it's always a good idea to explore your data more, besides only apply goal-oriented supervised data mining methods. And as you explore, you learn more about your data. You may find new business questions or new ways of applying supervised learning. So that you have learned in the class that in past data mining classes that the two unsupervised data mining methods, association rule mining and clustering, can be very useful for exploratory data mining. And when your data sets contain words extracted from text, you can apply association rule mining and the other clustering unsupervised method to this type of structured data set, even though they are related to words. And we have some exercises, or some of you have exercises before about this too. And so we won't use tutorials or demo to go over this, but I just want to quickly mention, since some of you are looking at projects that involve text mining. And with association rules, then it's I think it's straightforward to think about that we can treat terms like n-grams, phrases, or one gram of terms as items in baskets. And we think about baskets may be formed by sentences, paragraphs, reviews, or whole documents, or just a subject, and to see words that frequently appear together within a basket. So since now we are already familiar with generating document term metrics, and the binary weight representation used in generating document term metrics can help produce the kind of sparse basket metrics that association rule mining algorithm or package like like a rule or a priori can be used. And when some of the research out there, or studies out there, have used this approach to determine whether there are certain interesting events or relationships in that can be discovered from text, such as blocks. For example, if some of the words are drug names, or medication names, and some other words are in the category of side effects. And if medications oftentimes found to be associated together with side effects, then there could be some concern with a high frequency of side effects when taking a drug. So this is an example of applying association rule mining to to text. The other common unsupervised method is clustering. And in the past, some of you may have used in other exercises to find groups of similar records. And if a record is a review, like we have uh, in the past tutorials and assignments, and also, or a record is a document, and the attributes are words, then using this type of input data, when you do clustering, essentially you're finding groups of similar documents and or similar reviews, and there are similar clustering methods such as k-means will determine that reviews or documents are similar because they use some similar words or use words similarly. But if we transpose the data frame of reviews and attributes in a way so that the input data now will use each row to correspond a term or a word or a phrase in your extracted from your corpus. And the columns or the attributes actually correspond to the documents in which the words were used or were associated with. So this is the transpose metrics of this type of input data, or the type of input data or document term metrics we already have. Using this type of input data, you can use clustering to also find groups of similar words, not just groups of similar reviews or similar documents, because this could be interesting in a lot of applications. And again, clustering using distance function that calculate distances between different instances based using attributes, which are documents. Then similar words grouped using clustering algorithm would means that these words appear similarly in documents. So some of the words that are grouped together, considered to be similar, they probably tend to appear in the document, in some of the documents together. And so for this hierarchical clustering that some of you haven't applied yet, has been used also very often for this, for clustering similar words. And otherwise, k-means is also still a good method to do this type of clustering. So this just to remind you that you could try the data mining methods you have with document term matrices that you have been generating so far. But mainly in tutorial 3B, we are interested in topic modeling. And it is also used in mostly in ways for unsupervised text mining. So here, topics are assumed to be unobserved, meaning that we don't know the topics of a document, or the topic of a document, or the main topics of a set of documents or a collection of documents. And because we may not have labels for them, so that's what we mean by unobserved, which are also mostly just called latent. And in the context of sentiment classification, on one hand, we can think of, well, if you're doing unsupervised sentiment classification, then you actually don't know the sentiments. So the sentiments of, for example, tweets, before you actually label them or try to classify them, they're unobserved, they're latent. So this could be a way of generating. So if we think of sentiments are the topics, unobserved topics of a collection of tweets or a collection of reviews, then we could possibly consider and try topic modeling algorithm to generate documents that belong to for example, to unobserved sentiment topics. But oftentimes, the users or adopters of topic modeling processes are interested in finding out not just sentiments, but some underlying themes that are running in the text. If your text use comments or reviews or tweets, and so this way, the use of this for identifying underlying themes of text is truly exploratory. You don't necessarily know what you're looking for. Like in our, if we're not necessarily looking for sentiments, but we're trying to see whether there's some themes. And some things can be, like there are some different ways of grouping movies, or because movies are often watched for July 4th or often watched for when around Christmas or Thanksgiving and so on. So this is some of the examples. And so topic modeling assumes that if the given a number of specified topics, for example, two, if I'm interested in sentiments, or I'm just exploring, I'll try 3, 4, 5, and try various numbers and see whether I can start to see some interesting themes. And so given the probabilities of topics where topics are unobserved, but words are observed because after the process of structuring unstructured content, we actually can see the words and we can filter the words, we can reduce the number of words. So we can clearly have statistics about the words. So those are observed. But if we assume that there's some probability that those observed words are used to describe each of the given unobserved topics, then based on this distribution and a very sophisticated iterative process of doing expectation and likelihood maximization, and various algorithms follow this type of process can generate the topics that the probabilities that a document or like a review describe each of those unobserved topics. So the probability that a document is describing, for example, a positive sentiment or a negative sentiment. And also it can identify, using the probabilities, we can select the topic that a document belongs to using by selecting the topic with the highest probability. And after the topic model is generated, there will also be a rank order of words or engrams or not that belong to each of the topic. And like I said, this is applied, and there's some good material out there to go into the methods, including a course right now in school computing is entirely about probabilistic modeling that's very, very related to this, as well as more methods. So the most common method came out in early 2000 that extended latent semantic analysis method. This method called latent Dirichlet allocation methods being one of the most popular algorithm is the most basic one. And building on this, there have been lots and lots of extensions and more and more are also available in to different users in either R but more in C++ or other languages. So like I said, we were focused on applying. So to quickly move on to tutorial 3B, I'll just use this slide to talk about what the code demonstrate is not is besides that it will generate topic models, but beyond that, we're trying to see how some twist of using topic models and evaluate the use of that. Since continuing with the sentiment classification, positive and negative sentiment classification task in tutorials 1 and 2 and sorry about this, tutorials and assignments 1 and 2. So we'll in tutorial 3B, we'll just mainly demonstrate the code to explain, examine and look into the potential to allocate documents to 2 latent topics. And that can be easily generated, it takes time. And then we can treat these topics as the sentiment labels learned using topic models in an unsupervised learning manner. And with the data sets that have actual labels, you can easily evaluate the effectiveness of this. We didn't directly evaluate whether the accuracy of the topics generated by the topic model. Instead, I did a little bit of twist, is to use also the topic probabilities that topic modeling algorithm generated. And even though it's only topic probabilities for 2 topics each, and for each document, we can still build and test some classification models using decision tree, using naive Bayesian and support vector machine in a way similar to tutorials 1 and 2, and see, because our data set has the labels, so we can do it. And I just, instead of using, or in addition to using bag of words, and the term frequency, document term frequencies of the bag of words to do supervised learning, we'll also consider topic probabilities. So, so in addition to what we normally have done using document term frequency metrics to do supervised learning, we will see one model building and testing, classification model building using decision tree, naive Bayesian, and support vector machine using these topic probabilities only. So it's a very thin data set for training and testing, and we can see how how it comes. I was just curious, and I thought I want to include the results. And then the other is to combine the topic probabilities with the document term frequency of bag of words and build classifier, and then see what happens. So let's go to the tutorial. Let me make sure we, similar to 3A, because I have already run this tutorial and kept some of the results. So if there's time-consuming part, such as building, such as LDA, building topic model can be about 5 minutes for 1,000 reviews. So I will skip for now, and then just show you some of the output and the results. So we're using movie one again, and this is the familiar code to input. Because of the twist that I did, I do want to use topic probabilities to build and test classification models using other classification using classification algorithm. So before I apply topic modeling algorithm or LDA, I still did the splitting like I did to produce train one, test two. So this is familiar. This is the topic, the LDA algorithm, and many other topic modeling algorithm use document term matrices as input. And specifically, most of them, and the ones we have tested so far, use term frequencies. And some have already indicated clearly errors that if you try to apply TF-IDF, because the algorithm doesn't take TF-IDF as input, even though sometime during the process, some of these functions or algorithm will generate TF-IDF to do some optimization. But in any case, the input should be term frequency. The weight type should be term frequencies in document term matrices. So, so this is also a similar process where for the train corpus, and similarly later on test one, test two corpus, once corpus is created, text processing is performed similarly. And we have tested many, some of you who have already started trying, and in our other testing, we also have tried various n-grams, and because they take longer time, in this tutorial, I just kept it to 1 gram. So 1 gram, and the term weight is term frequency. So the document term matrix is very simple for train, because so far we don't have dictionary yet. So this is the name of the document term matrix for train. A little bit longish to with the TF there. We don't have to keep it there if we don't want to. This is in this tutorial, I use 90% sparsity and to reduce it to about 500, actually about 511 terms. So I thought we'll take a look, because later on you'll see that this will be the words, and the term weights of these words will be used to build topic models, and we have about 511 of them. And then this bag of words created becomes a dictionary later on when we build document term metrics for test one data set. So this is the dictionary, and similarly for test two data set. Okay, this is the document term metrics for test two. And since we're going to build classifier, so I use this opportunity to also create the input files for the classification model building process that will simply just use backup words, and this way we can have a comparison. So I have this for test two, and earlier on I skipped the same command for test one and train data. So since this is similar to code we have seen for a long time, I'm not going to run it, and we already have the data the input files created and the document term matrices created that we can now use for topic modeling and then later on classification building. So this is topic modeling for trained data. The library is topic models, and I have already loaded it earlier on. And there are many there are other packages. Specific LDA is one of the other popular one. And but topic models also have some other algorithm that in research projects we've been testing and very interesting. We won't have time to introduce some of them, but I think accessing this package and reading the documents and publications about it could maybe give you some more information about other topic modeling algorithms that you can try. So these are, and I won't explain this input parameters. All of them are used in the Gibbs sampling, which is a Markov chain Monte Carlo distribution generation processes to generate observations in the generative process and to iteratively find optimal parameters and distributions, the underlying distributions that describe word and topic and document associations. So some of the sample codes have tried a few similar ones, and these are some good ones to give it a try. For our interests related to sentiment classification, we also need a number of topics, and K has been used for a lot of input parameters. Here, K is the number of topics, latent topics. So once that is the initial parameters done, we are almost ready to use the function LDA. In some other, using some other corpus, we get problems which is very, very sparse. So we get problems if a row is 0 or it could be redundant. So just to avoid confusing this topic modeling process, and you can consider to include this code to remove any rows that have exclusively only zeros as term frequency for every single term. This is what this does. And in our data set, in our tutorials and also in IMDb, it's not that sparse, especially once we apply sparsity. So it's not a problem here. In any case, I also have run it. So this is the topic modeling function that this is the line that calls this function, and this is the document term metrics. That after we have removed 0 terms, so each of the document term metrics now has an even longer name. So this is the document term metrics from here, and which actually use an earlier document term matrix. We indicate remove sparsity from the sparse terms from the document term matrix. K is equal to 2 as given, and the methods called Gibbs sampling for the distribution generation. And there's a list of control parameters which fit in this parameters that was set to these values here, including best equals to the default value true in this list to this method. So once this is run for 1,000 records and 511 features in the document term metrics, it took about 5 minutes, a little bit, maybe a little bit longer. So we won't run it now since it's already been done. Instead, let's call the structure. Take a look at the structure of the result of topic model, this LDA function, which is the topic model. It has many slots, including some of the parameters that were set, and also such as K is here, And there's also some initial other internal parameters like alpha, delta, that are used for throughout the process by the underlying distributions. And the terms are the bag of words in the document term matrix. So it's 511. Our documents is 1000 recorded here, and beta is another parameters as being trained during the topic modeling purpose. Gamma is at the end of the process, outputs the probability that each document belongs to one of the two latent topics. And it may be our sentiment, it may be some other topics, but we can give it a try, see whether it can be used to help us learn the sentiments. And then, so once this is done, we can start to use the output, such as the terms associated with the different topics and the probabilities that, like gamma, we looked at earlier on, the probability that a document belongs to one of the K latent topics. And using the function topics on top of this topic model generated, and we can also learn or find out the topic with the highest gamma or probability a document belongs to. So in this code, in your tutorial code, we generate output, write it out. It's kind of long, so showing in this in Word, in your output result or in console can take up a lot of space. So that's being output, and we can take a look at those. So for example, this is for the train data that we did. If you just want to do unsupervised learning, by the way, you can just apply LDA to the whole data set and assume these two topics are the sentiments and give it a try. And that's not what I did, what we did in this tutorial 3B. Instead, we're kind of training and testing. And so topic models are built for, this one is for trained data only for 1000 of them. So this first column is the number of documents. The second column indicates the topic as this document assigned to. So topic 2, topic 1, and then later on we can see whether this will actually help us learn sentiments. So this one has 1000 of them. And this one is the one that have topic probability. So for example, the first document was assigned to topic 2 because it has slightly higher probability, and topic 2 also, topic 1. So it is not a very, the two, each document has sometimes hard to find very distinct probabilities for a document to belong to different different topics like this. This is a bit nicer, but some of this is really tough, very, very close. The other output is the top terms, rank order terms associated with each topic. So the rows are just term rank number, rank 1, rank 2. So it had nothing to do with documents. In this one, we output actually 200 of those. It's not this one. Okay, this one is the 200. this one. And we have seen these terms in the background words, and the same term can appear in multiple, it's just different order. From looking at this, it's really hard to see whether they can help identify sentiments. I think to me, maybe this topic too is a little bit easier when I see bad and enough, though, oh, no, and nothing, after it has been stamped, and way down is where we start to say, oh, this is obvious bore, worst. I mean, no, if we don't worry about negation, waste, miss, I think some of these terms we already saw in earlier tutorials that they could have some predictive power, but the others are good is here and great is here. It's not very easy. So looking at topic modeling results can be difficult. Like I said, topic modeling is not necessarily used for unsupervised classification. And if you just want to explore the underlying theme, in this example, using same data set, actually similar data set, IMDb data set, create where for 6 topics. And I think some of the topics start to see something. For example, topic 6, the words like action, kill, and run, and sex, and game, shot, and car death seem like action movies. And this one, topic 5, effect and special effect, war, horror, and dark. It seems to be war and horror related. This one is not a bad one. Topic 4, I kind of feel this. It's very down to earth about family, man, woman, husband, wife, American girl, emotion, and relationship, father, mother. A lot of these are all mentioned and seem to be maybe drama and very family oriented, or relationship oriented. Topic 3, some of the words are more unique compared to other topics, are like music and laugh and comedy and entertain and comic and joke, humor. Kid could be comedy type or music type of movie. And the other 2, not always easy, but this could be mystery, power, belief, possibility, wonder. The first one is tough for me, but has place, money, talk, and some of these are more unique in this than others. So could possibly use this to discover themes of your content that way. So coming back to complete this tutorial, which the twist I mentioned is to use the topic probabilities that being stored from this topic model and put this together with the supervised the sentiment labels, true sentiment labels in the data set, and create some output file, create this new metrics that can be used to generate output file, input file, sorry, to classify a building. So, so this is the code for doing this. For test 1, earlier on, let me go this way. Earlier on, I did this for train before, and to prepare the train data set. And in order to have the topic probabilities for test 1 and test 2, so I also apply LDA to test 1 using document term metrics after this has been executed, has been applied to test 1 document term metrics to remove the instances with zeros in all the term weights. And to do, like I say, to do unsupervised sentiment classification, you don't necessarily have to have train, test, and test. And this one is to also to use the output in a twist using the probabilities. So to save time, we won't run this because this one has LDA. Each will take about 3-4 minutes for test 1 and for test 2. This one is for benchmark. We'll take the backup word term frequency and prepare. This data set was prepared using document term frequency with backup words that was built using 90% sparsity removal in the trained data. So I can quickly run it because it won't take too long. So it actually may take a little while because it is 511. But as you can see, this is decision tree. Test 1, test 2 is roughly about 68 and 65. Naive Bayesian takes a little while and just right around 70 and percent for test 1, and test 2 should be a little bit, maybe a little bit. So this is test 2, very, very close. And KSVM, so let me roll back. This is test 2 using naive Bayesian. And this is test 1 with KSVM, test 2 with KSVM. So these classifiers, these testing results were evaluating the models built using 511 words in the backup words, and the term frequency, the term weight type was term frequency. So not bad, better. It's good sparsity. 511 terms have given push up KSVM to 78, not over 80%, such as 95% sparsity in tutorial 3A or earlier other assignments. And so now this is the part where I use the input data set for trained data that build with only 2 besides the label, sentiment label. This input data set contains 2 other columns of the probabilities of this document, each document for topic 1 and topic 2. So this was generated using LDA. So it's a very thin input file. We see whether this could potentially be used. And no, it is probably generated using document term metrics. So in a way, you can think of this almost as a way to reduce dimensions to 2 dimensions. I actually tried many other dimensions. It turned out that I found 2 dimensions, reduce 511 to 2 this way. Doesn't give me very good performance, but not the worst. So it's kind of interesting. And this should run very fast. And this is the second last set of classification and testing results that we will run. So let me roll back to the results from C3. It actually improved C3 performance and very even cross, and accuracy, recall, precision, and F measure. It's improved slightly, improved C3 slightly over 511 backup words, and this runs fast. But both naive Bayesian and KSVM, we lost accuracy and performance, and it's less even and a bit more but less over, slightly, no, not as much of worry on overfitting, a little bit more narrow difference. And so that's kind of interesting. The last one just combined these 2 columns of probabilities with 511 backup words. So it's a little bit slower. It's back to still relying on using backup words, and but we already have gotten decision tree. So decision tree performance has improved and slightly, and it turned out that the result just slightly improved for SVM, and we and also slightly improve for naive Bayesian. So you can see we push up to 71 and 70.6, and this one push from 77 to 78, but we drop 1 from 78 to close to 78, and but less overfitting. They're all very close. So this is the interesting twist of the use of topic probabilities generated by topic model. That's the end of tutorial 3B. Thank you. Bye.